Today we will be continuing our talk on one-dimensional kinematics. We just looked at distance and displacement and the differences between them on Monday, the other day. Today we will continue that on, and the topic will be speed. And in the famous words of Lightning McQueen, I am speed. I prefer to be velocity, so you can be speed all you want. We normally think of speed as how fast you're going, which is in some ways not far off, but it doesn't tell us the whole story. What we usually do in calculations is actually calculating average speed. That is, you take your total distance and divide it by the time that it took you. That's your average speed. We should know, as you're driving down a highway, your speed is not constant, even if you put the cruise control on. You go up a hill, your car will naturally slow down. And then it goes down the hill and it naturally speeds up. Thanks, gravity. And those are things that will play small variations in your average speed, but they're not going to be seen when you do your calculation. They could be seen when you look at the data more closely. The units that are used can be distance over time. Traditionally, kilometers per hour, very common one, because that's what's on our speedometers in the United States, that and miles per hour. The more common one in physics is meters per second. So being able to convert from kilometers per hour into meters per second becomes very necessary sometimes. You could even have centimeters per minute if you wanted to. But a lot of times your answers on, say, your homework that is available, that about 3 people have started. We haven't covered everything in those homework yet either. In case you're like, how do I do that? We haven't covered it yet. But some of the simple stuff is there. Is usually going to be kilometers per hour or meters per second. Okay. Since we have an equation, it'd probably be a good idea to put said equation on an equation sheet. Now, whether you put an average speed or velocity, that's up to you, because essentially you're dealing with the same thing. Just that velocity has direction. Because velocity is a magnitude aspect along with that directional aspect as well. That's why I put the little red arrow there, because that's how we signify or indicate velocity, usually with the red arrow. Velocity is speed with direction. That's why we use displacement. Because displacement is distance, but with a direction. Sometimes the direction is down the ramp or up the ramp to indicate what maybe some other information there. It's not always going to be directional, say, on a compass. The x that we have here could be change in the y just as well. And you would have the same thing. It's just that it would be the velocity changing in the y direction. And because it's displacement, any of the variables that we use for displacement can also be used. And if I remember right, there was a lot of them that we had. But I definitely would, if I haven't written already, the velocity equation in that. Now, sometimes you'll even see the velocity equation written out this way. Where it's more linear. Distance is equal to velocity times time. Where you could also write it as y but sometimes it's even written out as that. Doesn't really matter which one we use as long as we have one that we are using consistently. And it's all, there's really no difference between these ones. They're just an algebraic manipulation. Now, we have to be careful when we talk about constant velocity. Because remember, the difference between speed and velocity is direction. You can have a constant speed, meaning not speeding up or not slowing down, but not have a constant velocity. Because remember, velocity has direction. If the direction is changing, the velocity is changing. Constant direction, straight line. Okay. If the speed or the direction is changing. Okay. Let's look at some examples of maybe how that would look. An object sitting there. Does it have constant speed? Yes, it does. It's just constantly what? Zero. And that's what a lot of times people get confused with. They're like, it can't be constant. It's not moving. Not moving is a constant. It's just constantly zero. Okay? What if it's moving on a straight line? Now we're going to take a little, like 1 second intervals here. It's on a straight line. The arrows themselves are not getting bigger. It's moving. It has constant speed. Does it also have constant velocity? Is it changing its direction? No. Easiest one. If I have a ball inside of a circle, at 1 second it's there. 1 second later, is the ball going to be in the same spot or on the straight line? No, 1 second later, that ball's there. And now the arrow's pointing in a different direction. Because it's pointing in a different direction, what has changed? The direction has changed. It might have a constant speed, but because the direction has changed, the velocity is now changed. What if I take one of these examples and I put the object on here. Try and get that same line there. Knowing what you know about driving a car, what should happen to that object 1 second later? Is the arrow going to get smaller or bigger? Smaller. Because gravity is quite the pain in the butt and slows things down when it goes up a hill, right? And it's not really changed its direction a whole lot, but because of gravity, it's slowing down. It has change in its velocity. What happens? We go the other way. What's going to happen to that arrow? It's going to get bigger because it's going to be doing what? It's going to be increasing its velocity or speed because it's getting faster, helping out by gravity. What about take an object and I throw it up in the air? Straight up in the air. What's going to happen in 1 second later? Is the arrow going to be bigger or smaller? Smaller. To the point when it reaches its apex, top, the arrow for a very small moment in time is going to be what? Essentially non-existent. Right? So there's a small moment in time, and we throw something up in the air that it just kind of it almost looks like it stalls out for just a small moment. And all that is just the changing of going up before it comes crashing down. Now, here's the fun thing. The arrows, if I drew them out properly, should be exactly the same. As the instant that it starts going up is going to be the arrow, or the velocity should be exactly the same the instant before it reaches that exact height that it was released from. So we have to be careful and really look at that. How is it changing? Is it changing? And a lot of times people say, well, it's not moving. Yeah, not moving is constant. It's just constantly zero. And be careful with that. So, graphically, let's take a look at this. Got a little fire truck there, moving across. Toy fire truck, since it's 60 centimeters, makes sense. 15 seconds. Some of you may or may not be able to do the velocity or the division in your head. But what is that going to look like on a graph? And this becomes another one of those fun things of visualizing things and looking at graphs and being able to look at a graph and go, okay, I can see what's happening with the motion, and you're not even there looking at the thing. But you're going to be able to figure some things out. Okay, so we have the 60-second intervals. So we're going to, what is that going to look like? Well, we'll put a position time graph together. Space things out real nice. Start is going to be our origin. Position time. Okay? That's what it's going to look like, that beginning part, right? That's what it looks like on the graph. 0, 0. Okay? What if it was moving before it got to the start line? Oh. We'll worry about that another day. Okay? It moves 60 centimeters in 15 seconds. Graphically speaking, we should be putting a dot where? If we had to do these graphing by hand, we have so many nice technology things now that we don't even bother thinking about it, but let's think about it anyway. Where should that first dot be? Okay, position 60, time 15, right? Rise, run. Put our dot there. Okay, looks real nice. Okay, 15 seconds later it goes an additional, and that's a big thing, an additional 60 centimeters. So do we put another dot at 60 and 15? No, because it's an additional amount. We add distance and time to put another dot at 120 and 30. Now it becomes one of those lovely things that, sometimes restaurants do. You remember connect the dots? You're like, connect the dots, la 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 la. Boom! Connects the dots, nice straight line. And those of us that have had enough math would call that a direct proportion, right? As one's going up, the other one's also doing what? Going up. Nice straight line. Woohoo! No curvature in that one. Don't worry, we'll get there. It means different things when there's a curvature. We see a straight line like this, okay, things are nice and constant. It's like they're supposed to be. Okay? So now, when we can look at things, we have to kind of interpret some graphs maybe. When we look at our graph, finally, the slope, rise over run, is the same as displacement over time. So your slope of your line is essentially your velocity. Because it is constant, doesn't matter where you're at. It's always going to be there. That would be probably not super great way of saying that it's instantaneous, because instantaneous means very small moment in time. Okay, we might see some small variations in some things. Instantaneous velocity is a completely different thing. It requires us to understand limits. Some of you, that brings up really bad memories. I get it. But what we look at it from is just from like okay, what is this equation telling us? Well, the limit as it approaches zero, meaning the time interval as it approaches zero, extremely small time intervals, we can kind of cheat and not use calculus by just saying, okay, we're just going to zoom in and zoom in and zoom in and zoom in, because you zoom in enough on a graph, a curved graph, eventually you're going to get very small graphs like this. The time interval might be extremely small, but that's ultimately what you would end up doing when you're solving for the area underneath a curved graph in calculus. Is you're cheating in a way that you have math skills that others don't, that you're able to kind of take that into account, the curvature into account. The rest of us with algebra, we'll just do this. So that's why it's kind of there. It's like, if you know calculus, physics can be very like, oh, this isn't that bad, and you're going to zip, zip, zip. Those of us without calculus go, oh, so I just have to do these couple extra steps? That's about it. The science doesn't change. It's what math you're using to get to that same answer, and ultimately you get to the same answer. So that's where, even though students in the past go on and have taken algebra-based physics and do well, even those that have gone on and taken calculus-based physics after this class have gone on and done well. It's because they have an understanding of the science, and they go, okay, I just need to figure out the math to apply here, and that's again, part of the goal with this class.